Welcome to Chapter 7. As you can see from the slide, we're going to be talking about samples. The last chapter had to do with populations, and this chapter is related to sampling. So we're going to talk about some of the differences with sampling compared to populations. Samples are obviously smaller than populations, but they can have a lot of similarities with regards to the distribution or what the curve looks like or what the frequency distribution looks like. We're going to talk about something called the central limit theorem, which I'll leave for a moment. So sampling, as we're well aware, is n minus 1. So it's the population, but smaller. It's a subset. So if you can see an example, they take 50 students from your college. You get a sample size of 50, which is not all of the students, and calculate the grade point averages, and you can infer from that grade point average what the grade point average is for all the students. So in this particular case, we have 4 as our population, and we have a sample of the values here, or so 18, 20, 22, and 24. And in this particular case, we have the standard deviation, which is also known as the standard error of the mean. So what it does is it's like standard deviation for the population, except it is standard error for the sample. So in this particular case, we assume that the population is normal or normally distributed. Previously, we would have used z-scores. So you can see the formula here. And we will not use z-scores a lot. We will use the t-scores. So we have the mean. You've seen these several times. We have the mean, but you can see that the standard deviation is very different between the two, even though they have the same mean. As the size of the sample increases, the sample will start to look closer and closer, or the curve, area underneath the curve, will start to look from the sample will get closer and closer to the actual population. So if you, it's very, to make it simple, if you had a class of 30 students and you sampled 2 students and asked them what they thought of the course, for those 2 students, that is an accurate result. But would you be comfortable stating that the results from 2 students out of 30 gives you a true picture? But now let's change that. Now you've sampled 7 students. 7 students fill out the course evaluation. Well, now the sample will be closer to the population. So if they thought the course was great or average or poor, you're going to get a more reliable result, which is going to come up in upcoming chapters. But also the distribution would look more like the full, like the population. So let's say the 7 becomes 17 out of 30, and then becomes 24 out of 30. And of course, if it's 29, it's going to be almost identical. So this, hopefully that makes it simpler to understand. Just basically, as the sample size gets larger, it looks more and more like the population, which makes a lot of sense. So in this particular case, you are given some information, and we're talking about a confidence interval. So to state that the class average is going to be 72%, it's highly unlikely the class average is going to be 72%. And by the way, I'm not using the example on the screen. What you're more likely to say, and engineers use this all the time, engineers call them tolerances, but saying the class average is going to be 72% plus or minus 5%. So 67 to 77. So I'm fairly confident that, I'm 95% confident that the class average will be between 67 and 77. That's all. That's what it does. And in this particular case, we want to find a interval. So you're going to, and you base it around the mean. So the interval contains 95% of the sample means, and there's a 5% chance that it is not, that the class average would not be between, say, 72 and 67 and 77. So to use these examples on the screen, you are going to say that the average is 368. The standard deviation is 25, and the sample size is 25. Sorry, the standard deviation is 15. My apologies. And the sample size is 25. So what we're trying to do is get give ourselves a range or wiggle room, whatever you want to call it. So we want to say that 95% of the sample is within this interval, confidence interval. And that means that 5% is not within the interval. So if it's symmetric and it's two-tailed, 2.5% is below and 2.5% is above. It can also be used to determine outliers. That if they're, remember outliers are extremely low or extremely large values. So if we say that this will cover 95% of the examples, we can say the other 5% are considered to be outliers. And so we're calculating, we have the Z-score, but we will mainly use T values. But the concept is the same. It's identical, except you use T instead of Z. So you can see that based on a sample size of 25, that 95% of this 95% chance, the actual average will be 362.12 up to 373.88. 2.5% of the time, the value will be less than 362.12, and 2.5% of the time, the value will be 373.88. So I sort of look at it this way. There's a 95% chance that the values are between those two numbers. There's a 5% chance that it's going to be outside. And we will use this in upcoming things to determine what the likelihood that you're correct or the likelihood that you're going to make a mistake. So applying the central limit theorem, you can see as long as the sample is approximately normal, because very rarely will you get a perfectly symmetrical sample, all right, or even perfectly symmetrical population. But as long as it's pretty close, it actually doesn't affect things that much. So what happens again is, as the sample size gets large enough, the sample mean becomes almost the same as the normal. And also the shape becomes almost the same as the normal. That's the point that we're trying to make in all of these slides so far. The larger the sample, the more it looks like the population. All right, and here's just another graph on it. As you can see on the bottom right-hand corner, the smaller sample starts to look closer to what would be considered to be a normal distribution. And in the past, they've used a standard of 30. We're not going to use that. The true way to do it. This was done as a sort of a hybrid because of limitations in the fact that we didn't have the technology that we have now. And we're going to simply say that anything less than the population is a sample. We used to use the fact 30 is the cutoff just because of lack of technology. But because we're using technology, and specifically Excel, we will use This is why we're going to use the t-scores instead of the z-scores. The z-scores are for populations, t-scores are for samples. But anything less than the population is a sample. So in this particular case, we're given the information again. We have a sample size of 36, a mean of 8, a standard deviation of 3, and what is the probability? It's going to be between 7.8 and 8.2. So minus 0.2 and plus 0.2. And we get a standard deviation of 0.5. And we plug this into our calculations, and we're going to use Excel for this. So this is to show you all this stuff at the top is taken away. By using the technology, we're doing it the way that industry does it, and we're taking all the way the tedium. There's a whole bunch of these things that are automated, and you can focus in on the really important things. Do I use T or Z? Use T. Always use T when you're working in industry, unless it's proportion, and we'll come across that. But that's what you need to focus in on, not these formulas and looking things up in tables like we used to use it. All right. So population proportion. All right. The proportion of the population having some characteristic. So this is used when, for example, what percentage of people talk on their cell phone while driving? What percentage of people have four-wheel drive in their cars? Things along this line. So to find the probability, just as we did in earlier chapters, you find the number of items that have that characteristic. So with the cell phone use, you would record the fact that 17 people were talking on their cell phone out of 50. So that would be 34%. 17 divided by 50, or 0.34. So, but you don't know, and it doesn't matter. You're trying to find the proportion / percentage. And so the proportion is between 0 and 1. The percentage is between 0% and 100%. And the proportion is, for our purposes, always assumed to be normally distributed. And for proportions, you use Z. And you can see how you can calculate the standard deviation. The pi symbol is the probability of, if you want to say success. 1 minus pi is the probability of failure. And in some textbooks, 1 minus pi is Q. But for our purposes, you have pi, which is probability of success that we just calculated. In the example that I just gave you, that's 17 out of 50, which is 34% in percentage, or 0.34. The value is for pi is 0.34, bracket 1 minus 0.34 in the formula on the bottom on the right, and all divided by the sample size, which is 50. And that will give you the standard deviation. So here's an example. So the political parties use this all the time, or pollsters use this all the time. And in this particular case, you see that the proposition is 40%, 0.4. And we want to find out the proportion that is between 0.4 and 0.45. We go through the calculations, and we can see that the standard deviation is 0.03464. We plug it into the formulas, and we find out that it's between 0, which is the mean, and a z-score of 1.44. And it's positive, so it's to the right. So here's a nice demonstration in the bottom left-hand corner of the colored area shows you in numbers. On the right in the shaded area on the right, it shows you 0.4251 is the area. So 42.51% of the area underneath the curve is between 0 standard deviations and 1.44. So there's a 42.51% chance that we're going to find the answer within that from 0.4 to 0.45. So we talked about sampling. We'll definitely get much more into the t-scores and stuff, but that I've mentioned several times. But this just gives you an introduction for the fact that you can use samples to approximate normal distributions for population. And the central limit theorem is critical. If we didn't have the central limit theorem, it would be a major hindrance, and that simply says the larger the sample, the more the sample looks or approximates the normal distribution. So hopefully I've made a few things clear, and obviously we'll go through some examples from this chapter.